Hello. We're going to take a quick look at searching and sorting, some simple algorithms that we see quite often pop up in computer science. Starting off with the simplest of these, which is a linear search. We're literally just going to look through each element of an array and try to find if a number is there or not. So let us get started. I'm going to include our usual suspects. And this is what we're working on. Okay, so let's make an array of 1,000 random numbers. So int array of 1,000 for I is 0, I less than 1,000. We will say array of I is some random number. Okay, now if we want to be able to find a random number, and there's only 1,000 of them, we probably want to be able to set everything in a range where there's a good chance the number actually shows up. So let's pick numbers from 0 to 999, so that way most numbers probably should show up at some point. Okay, we're going to use a linear search to find and return the index of a number you choose to find, or output that the number isn't there. So once again, we'll just do the same loop for each element of the array. And let's say that we're looking for a int target. And let's say we're just looking for 100. If array I is the target, and I suppose we want to put this in a function. So let's actually do that. I'm going to grab my code, and we're going to make a function called bool int linear search. And it's going to need to take an array, and it's going to need to take a target, and we'll also need the size of the array. And so here, if we go through our array and we find our target, then we can return I. Otherwise, we can output did not find and return -1, just as a code to indicate that we weren't able to do it. And we will output the value 1,000 is at index, and then we will call linear search. We will pass it our array and our target and our size, and we'll see what happens. So when I compile, oh, what did we mess up? Oh, we didn't declare the target because our target is 1,000. So there we go. Sorry, 100. It was 100. There we go. Okay. Let's see. Oh, yes. In size, we need to say how big it is, and our array is size 1,000. All right. Third try. There we go. And when we run it, hooray, the value 1,000 is at index 54. Now, because I didn't seed my random number generator, it's always going to be there. So let's actually make sure that we handle that by including seedtime and seeding our random number generator. So now that it's seeded, we should actually see different results. Oh, did not find. 736. Did not find. 313. And sometimes it'll be there, sometimes it won't. Where we have random numbers, so there's no guarantee the element will be present. But we've managed to implement a simple linear search. All right, let's move on to the next one. Okay. So now we're looking at binary search. Now for binary search, we need a sorted array of 100 numbers. So let's duplicate this. Now, we need a sorted array of 1,000 numbers. So rather than making a random number, what I think we're going to do is we're going to start with array 0 is going to be 0. And then every number after is going to be array I minus 1 plus a random number from 0, 0 to 2. So sometimes we won't have it go up, sometimes it'll go up by 1, sometimes it'll go up by 2, but it'll be random. And now this makes sure that we have a sorted array. So just to sort of show that, first of all, let's set up some more variables to make things a little cleaner. Int size equals 1,000, and now I can replace 1,000 with the size. And also int target equals 100, and that will be my target. Now, I haven't done the binary search yet, but just to demonstrate that this actually works, what I want to do is comment this out for now. And let's make sure we can print out everything in our array and ensure it's actually sorted. I suppose I can actually just use the same loop. And we'll just output array I with a new line. Compiling example 2 and running it. So we can see we got, looks like about 1,000 numbers, which is what we should have. And you can see sometimes they go up, sometimes they stay the same. But on average, they do go up by about 1, and we don't quite reach 1,000, but that's because we got some duplicates in here. Now, we got a sorted array of 1,000 numbers, but now instead of doing a linear search, we want to do a binary search. So our binary search is going to be a little different, but we'll start with the same base point and make some changes. So instead of a linear search, it's a binary search. We're not going to look at everything. We are potentially not going to find it, but the way that we're going to look is we're going to start by looking at the middle. So we're going to have a start point and an end point. So our start point is going to be 0, and our end point is going to be size minus 1. And the reason I've chose these is because these are the indices that set the earliest and the last points in which the number we're looking for could be. So the earliest place it could show up in the array is at index 0, and the last place it could show up is at size minus 1. Now what we're going to do is we are going to look at the middle point, so int mid, which is halfway between the start and the end, and we're going to check 3 things. If array at the middle is the target, then we have found it. And we can just return mid. Nice. Otherwise, one possibility is that it is less than the target. Less. If that's the case, and the target is bigger than what we're looking for, that means it can't show up anywhere on the left side of this array. All of the lower numbers below the middle point can't possibly have what we're looking for, which means that we can update the earliest place it could show up, which is mid plus 1. And our last possibility is that the array, I guess I can do else if. The middle element of the array is bigger than the target, in which case it has to be on the lower end. So the last place it could show up is mid minus 1. Now we want to do this over and over and over as long as end is greater or equal to the start. As long as there's still more elements we can check, we want to keep updating the middle point, checking to see if that's what we're looking for, and then at the end of it, we either will find it or we won't. So let's still print out everything so we can actually see if the thing is there. And we're going to check to see if the value of the target is inside of our array. Compile and go. And it says 100 was not there. Is that the case? Let's see. Right, it goes from 99 to 101, so we didn't find it. Let's try it again. At index 101, let's go up. Hey, look, there it is. Now, the interesting part of this is how fast does this actually go? With linear search, it's actually very easy to see. The amount of times that we have to go through this loop is just what position it's in. If it's in the 100th position, then we have to go 100 times. If it's in the 700th position, we have to go 700 times. With our binary search, though, let's see how many times this loop goes. I'm just going to put a message that says loop is running. We found it at index 112, and we only had to go 1, 2, 3, 4, 5, 6, 7, 8 times through the loop, and then we found it. This is a lot faster than 112 times. So binary search is very nice because as long as we have a sorted array, it's much quicker to just cut the array in half every time for what we're looking for, rather than having to look at each one independently until we find what we're after. All right, now we can move on to sorting. Okay, bubble sort. So we're trying to bubble to the top or the bottom, depending on how you're organizing it. Each number one at a time until all of them have been moved into the correct position. So we'll run this, and I encourage you to try putting it into Python Tutor to see how it works, but we're just going to implement it for an array of 5 random numbers. I'm gonna copy it just so that I don't have to copy all of the boilerplate stuff, but we're gonna get rid of most of what's here. Don't need the binary search. We're gonna hold on to some of these things because we do want to have something to randomly generate an array, although I don't think we need to make it incremental. We can just pick a random number from 1 to 1,000 because we're trying to sort this into order. So we'll stick with random numbers from 1 to the size. Now, and we can get rid of this too. Okay, bubble sort. So this is a void function. It's called bubble sort. It's going to take our array that we're going to sort, and it's also going to take the size of that array. And now, how is this going to work? Basically, what we're going to do is we're going to compare every pair of numbers in our array. And if we find any of them are out of order, we're going to swap them so that they are switched in their position. If we go through the whole array and nothing was swapped, that means it's in order and we're done. But if we swapped anything, we need to do the whole process again. So I'm going to have a bool called swapped. Initially, it's going to be true. While something was swapped, we're going to set swap to false. And now as we go through our bubble sort, we're going to see, do we have to swap anything in our array? If we do, then we have more work to do. And if we don't have to swap anything, then great, we're done. Now, what are we swapping? Well, we're going to go through from the beginning up to size -1. And the reason I want to go up to size -1 is that I want to compare each element with the number after it. Except there's nothing after the last element, so I don't want to compare that to anything after it. Now, let's check to see, is array I greater than array I plus 1? If it is, they're out of order, and I should swap them. And to swap them, I'll just make a temporary variable, which is array I. Array I will become array I plus 1, and array I plus 1 will become I. If you're not sure why I took these steps, I encourage you to write this out. Take a small array of 5 numbers, literally organize what steps happen with this process, and that might help you see why I'm making these steps that are in here. Okay, so if that's the case, that I have swapped something, then swapped now needs to be true. And eventually we will go through and we won't have swapped something, and then we'll be done. Now, just since we're working with a size 5, which is pretty simple, we're going to bubble sort our array of size 5. and we'll print out everything in our array. Let's try it out. 00144, and that's in sorted order. 01134 in sorted order. And it looks like it is sorting everything nice and cleanly. Okay, so this is our bubble sort, but this is the worst way we can sort. Well, not the worst, but it's not a great way to sort. We can do better, so let's try it out. Now we're going to give a look to selection sort. So with selection sort, we're going to take a slightly different process where basically we are going to grab the smallest element we haven't picked out yet, and put that into the one part of the array. Essentially, we're going to grab the smallest thing and put it at the beginning. Then we'll grab the second smallest thing and put that in second. Then we'll grab the third smallest thing and put that in third, until we've gone through the whole array. So let's try this out. I'm going to copy this again. Okay, so I want to do a selection sort. The process here is a little different. So let's think about what we're going to do. So we want to grab the next smallest element, swap it into the correct position, repeat until all elements have been grabbed. Okay, so we're going to need some variables to help us keep track of what we're doing. So first of all, I want to keep track of the index where we're going to swap stuff next. So we'll call that min index, and it's going to start as 0 because that's the first place I want to put something. Now I need to go through my array and find what is the smallest number that I can work with. So I is 0. I is not 0. I is going to be min index because I don't want to check anything before that. Everything before that's already sorted. I don't need to touch it. But I is going to start out as the minimum index, and it's go up to the size. And we're going to check to see if array at the at array I is smaller than array at the min index. If that's the case, I have a new candidate for what should go there. So I suppose I could swap them right now. There doesn't seem to be much of a problem with that. Is there? No, let's give that a go. So same sort of scenario as before with swapping, except instead of I plus 1, we're swapping at min index. So this means that we're going to do a little bit more swapping than necessary. And in fact, I may not want to do this because it's a little bit inefficient. So what we're going to do instead is we're going to keep track of the smallest, at least what we think is the smallest. So int smallest, and we're going to start out with it being, let's see, can I do it at min index? Yeah, sure. If we find something smaller, then I don't know, this isn't really what I want to do. Let's think this through for a second. So my idea is, going back to here, I want to go through and find, supposing this is the index where my minimum number is going to go. I want to go through and find the actual smallest number. Here's the actual smallest number. When I find it, I want to swap it with this 7. And so here's the sorted part, and here's the unsorted part. Then I have a new minimum index. That's going to be here. I still want to go through, and I still want to find the smallest thing, and I have to swap that with the minimum index. So I think I don't want to compare to min index. I think what I want to do is compare to the smallest. And what I'm going to do is I'm going to constantly update any time that I find a number I think is smaller than the one I've seen. So starting off by assuming the first one is the smallest. I'll then keep going, and if I find anything that is smaller than that, I will say, okay, this is our new candidate for what could be the smallest thing. And once I've gone through this entire list, now I can say array, and now I can do my swap. And here I swap array smallest with array min index. And now this that I've written so far is nice, except it's only going to do this once. I need to do this once for every time that I have, once for every element in the array. So we're going to do this while min index is less than the size. And after we swap, min index will go up by 1. So let's do a selection sort. And just to see this, let's first of all make sure everything works, or at least looks like it works. Oh, we have a mistake. Smallest was not declared in this scope. And that's over... Ah, yes. So I need to set up my smallest over here. There we go. Let's try that again. And run it. Hey, it looks like it's sorting. It's a good sign. Let's give it a slightly bigger list to make sure it's actually sorting properly. Yep, looks like it's all nice and sorted order. So we now have an algorithm that is going to run a loop that runs for every element. And then it's going to look through for each of those elements and compare, is there anything smaller than the first one that I have? And if so, it's going to put that in the right position and move on. And it's slowly going to build a sorted array. Now, I encourage you to try this out and put it into Python Tutor, but the last thing I want to do is I want to compare these two programs. So what we'll do is we're going to run this with a fairly big array. So we're going to get rid of this here. That prints it out. We've seen that it works. And let's say that we do this with 10,000 numbers. When I compile and run this, it takes a second. Not a noticeable amount of time, but if I do 100,000, you can see it takes a little bit to go through, right? We're actually waiting here. Waiting, waiting, waiting. La, la, la. It took a little bit of time to get there. And now what I want to do is I want to compare, is selection sort or bubble sort faster? And to know, what I'm going to do is I'm actually going to time ./a.out. And what this will do is it will tell me how much time does it take to actually complete my program. So it took me 10 seconds to run a selection sort for 100,000 numbers. And if I do 10,000 numbers, I think it's going to be pretty quick. 0.1 seconds, real fast. Let's try with bubble sort. Hmm, 0.4 seconds for running with 10,000 numbers. Seems to be pretty consistent on that. And what about for 100,000? So here we may have to wait a little while. But the prediction that I'm going to have is that I think bubble sort is going to be slower than selection sort. And the reason for that has to do with something called time complexity. And it's the fact that some algorithms, some ways of solving problems just happen to be faster than others because of the approach that you take. Turns out actually both of these algorithms are not really optimal for sorting. They're ones that are very easy to write. You saw it didn't take me that many lines of code to do it. But that comes at the expense of the amount of times a computer has to actually process things is significantly longer. And in fact, you can see I'm still kind of waiting for this bubble sort thing to wrap up. Now remember, it took us only 10 seconds to do this first selection sort. I'm still sitting here waiting for bubble sort to finish. And this is, again, running on actually a very fast computer. And it took us, here we go, 53 seconds to sort those 100,000 numbers. Now, 100,000 may sound like a big amount, especially if we're talking, dollars. But to a computer, 100,000 is actually really small. And I can write, I think, myself, faster algorithms than the ones I'm showing here that will do sorting. But because these implementations are quite inefficient, you see it's actually not super great. So I encourage you to try looking up other sorting algorithms out there. There are some that are perhaps more complicated than you might be able to implement, but you will see that if you're able to get some of those to work, they can go way faster than what we have done today. So that's it for searching and sorting. Hopefully you found this video to be useful, and I look forward to seeing you in the next one. Take care.